Hey everybody, welcome back. So we've been talking about coordinate systems, and we've talked a little bit about rotation, translation. So far, the coordinate systems we've been looking at the Earth-centered, Earth-fixed, which are the X, Y, Z coordinates. And then we've also looked at geocentric and geodetic coordinates. So I'll say geodetic or geocentric. And just for the geodetic case, that was phi or latitude, geodetic latitude, longitude, and height, ellipsoid height. Today, we're going to talk about the local geodetic horizon, or LGH coordinates. And so the LGH coordinates are what we're used to seeing as the ENU, or easting, northing, and up. So easting, northing, and up. And those are the coordinates of our local geodetic horizon system. So it's called local geodetic horizon because it's a local system. We use it for a small region. And in the local geodetic horizon system, these are the axes. There we go. I have an image here that may help with visualization before I get on to my totally awesome drawings. So this is what's going on. So our ENU, our local geodetic horizon, is this. I'm erasing part of it. I don't want to do that. So here is our local geodetic horizon plane. That's a really thick red line. I probably shouldn't have made that so thick, but and the axes that we use are the so we have the up axis here. And if we were to extend it, what the up axis is that is the extension of the geodetic latitude, or the geodetic latitude of our origin here. So here's our origin. And if we were to extend this, this would be a geodetic latitude. And I'm going to draw that out so it makes more sense. And then we would have our northing axis, which aligns with the meridian going through the point of our origin, pointing toward the pole. We have our pole here. And then we have our local easting, which is simply a perpendicular to our northing axis. So that's a perpendicular. And that's what's going on. And our goal is to perform rotations and translations which align our ENU axes to our XYZ axes. And that'll transform our coordinates from the ENU coordinates to the XYZ coordinates. And let me shrinkify this, go back to the whiteboard, and I'm going to bring over my drawing here. And I'm going to make it pretty big so I can draw on it. So here's what's going on. With any ellipse we have, or ellipsoid, so here's our pole, and this would be our z-axis, and we're looking laterally, right? So looking laterally at the ellipsoid. And this would be the plane of the equator. And on an ellipsoid, as we've discussed, we have our local geodetic, or our geodetic latitude. And as we've stated, if we extend that geodetic latitude, that is the up axis of our local geodetic horizon. So that's looking laterally at that plane that we were just looking at. So that's our local geodetic horizon. So if you were standing at the origin, that is where our plane touches the surface of the ellipsoid. If you were standing at that origin, if you were to look straight vertical up, then that is up. And it's the extension of that geodetic latitude. With the geodetic latitude, so here's our phi, that's geodetic latitude. And if I were to draw an axis that's parallel to my z-axis, then it's easy to visualize what we need to do. So what we need to do, so there's a parallel to my z-axis, parallel. And we know that this is a perpendicular, right? So our phi it should be easy to convince ourselves that this is 90 minus phi. And if I were to likewise draw the parallel to the plane of the equator, that would be, change colors. Here. So that's parallel to the plane of the equator. And if we do that, it's easy to see that we have our angle here is phi. And then this is 90 minus phi, and that's important because from inspection we can tell that that is the angle we need to rotate our axis system to align align our up. This is our up, or our u, to align our u with the z-axis here. We have to go through an angle of 90 minus phi, but really what we're doing, we need to do a minus 90 minus phi, and that will bring the axis up this way. And whenever we're talking about a rotation, we need to know what we're rotating on. So at the origin of my ENU system here, what that is we can't see it in this drawing, but that is our easting axis coming straight at us. And what we're rotating is the plane of our local geodetic horizon, pivoting on that easting axis, that E axis. I hope that makes sense. So if I pivot this U, and this would be the N axis, and E would be coming straight out at us. I can't really draw a straight out at us, E. That's what we're rotating our U axis on by negative 90 minus phi. So, boy, this is really hard to draw, but I'm going to write down here on the bottom left, we want to rotate the U axis about the E axis to align the u-axis with the z-axis. So in other words, we must rotate the system, I'm going to say the ENU system, by negative 90 minus v, about the e-axis. And when we went through those rotation matrices, that would be our R3. Our rotation, we used gamma. Well, gamma here is equal to negative 90 minus v. Just an angle, that's all it is. So that would be one of the rotations we're going to perform. And as always, I'm going to go through the theory first, and then I'll do an example, and hopefully I'll have time to get completely through an example in this lecture. I may have to finish next time. So if I were to demonstrate, if my fingers were the here's the up axis, here's the n axis, which is aligned with the meridian, right? I'm just doing this until the u-axis is perfectly parallel with the z-axis. And that's the negative 90 minus v. So that is one rotation we need to perform. And let me scoot this up. Now let's look top down. So top down, we're looking down at the pole. And see if I can draw. Looking down on the ellipsoid, it looks like a circle. And there, a circle. And we have our x and y axes. Now we're looking at the ellipsoid right now. We have our x and y axes. There's x. So this is x in the positive, x negative, and I can... There's the y-axis. So we're looking at the plane of the equator, essentially. So y positive, y negative. And we have our point P somewhere here. This is our origin of our ENU system. I'm going to call it, what do I want to call it? I'm going to call it P. I'll say P is the origin of our LGH, I'll use them these interchangeably, or ENU system. And if I were to draw a line from the z-axis, or the center of the Earth, a projection from the center of the Earth. So I'm drawing a line from the z-axis to out to my point. We know what that angle is, don't we? Come on, stick. Going back to the beginning of the term, this angle is lambda. That's our longitude, right? Well, if that is our line of longitude going through our point of origin in our ENU system, remember we said that was our northing, our n-axis, right? It's pointed toward the pointed toward the pole because we're looking top down on this. So there we go. So it's aligned with our line of longitude through our origin. And then our e-axis would be perpendicular to that. So, and that makes sense, right? At that point, exactly at that point, the direction east and west is perpendicular to our northing axis. So that's our e-axis. We've already rotated, or assuming we've already rotated, so that the z-axis, which in our diagram is coming straight at us from the center of our xy axes. So our z-axis is here coming straight at us. And our u-axis is now here coming straight out at us, right? So now what we want to do, we want to align the e-axis with, there's no e on that, the x-axis. So how do we do that? Well, just like before, if I were to imagine my x and y axes up here at the origin, then we can translate our angles should get these to stay dark. There we go. And so here is the, the y-axis is parallel to the, so this would be our y and this would be our x. The angles that we have here are, so here's our 90 minus lambda. And this would be lambda. This also would be lambda. So from inspection, we can look at our picture and we can say, okay, if I want this E to rotate around all the way to the x-axis, I'm going to have to go lambda and then another 90 degrees. But think about it. We are rotating our axes clockwise direction, right? Which is negative. So we need to go minus lambda. Let's see, we need to go, I'll write it down here. We need to rotate minus lambda and another minus 90 degrees. So in effect, we're rotating minus, what are we rotating? We're rotating minus lambda minus 90. Which, if I pull that negative out, it's the same as minus lambda plus 90. Same thing. So you can use either form, right? So what would probably help is if you actually drew these sketches on your own, so you can see these rotations and how they work. Probably my drawings are a little messy, but if you draw this out on your own, you'll see the relationships of those angles. And by the way, if you guys hear dogs barking, I have a house full of dogs right now. I'm dog sitting. And they are rambunctious puppies, and they're, and then my dog's super loud too. So they're all kind of riling each other up. So I apologize for that in advance. And so let me get some more room here, and I'll kind of summarize that second rotation. In total, let me draw my circle again. So in total for this rotation, a rotation of minus lambda minus 90, or minus the quantity of lambda plus 90. So that's the amount of rotation, and that will align the positive e-axis with the positive x-axis. And then note that since the angles are cyclic, meaning that once you go measure an angle through a full circle, then the degrees start over again, right? So since they're cyclic, we could equivalently use (270) minus lambda. Same thing. That equals minus lambda plus 90, minus the quantity lambda plus 90. And we would get the same result. So once we have performed those two rotations, we would have a situation where we have there's our y-axis and our x-axis, and then up here we have our point P. We performed our axes, so the z-axis and the x-axis are aligned, and now the e-axis and the n-axis so this is our y-axis, our x-axis, this is our n-axis, and this is our e-axis. And notice that they are aligned now. The E positive is parallel to the X positive. And that's what that does for us. The last thing we need to do is to translate. And what do we need to translate by? Well, we need to translate so that the axes are coincident with each other. So that is this amount here. And that is t. That's our translation vector, right? And what you'll notice is the translation vector is equal to the xyz coordinates of the origin of my ENU system, right? So x, y, z. The origin, nothing about the origin has changed. All we've done is rotate. We haven't translated anything, and everything we've rotated has been about a line that includes the origin. So the origin is not going to change its xyz coordinates. My x looks like a gamma there. So that's the xyz of the origin, which is equal, if I make it a vector, that's my t. Actually, it's my t prime because of the direction we're going. So t, or t prime, since we're rotated, our axes are aligned completely with our XYZ system. Now our t vector, or I'll say our t prime vector, equals the opposite of the t vector, because now we're aligned. We've already done all the rotations. So now we don't have to use that derivation of the t prime vector, which is pretty nice. That'll come in handy. And I'll just reiterate here that my z-axis, if my z-axis is, I don't know, I'm going to make it magenta. Our z-axis would be here coming straight out at us, and our u-axis, since it's aligned with the z-axis, would be here coming straight out axis. So our axes are perfectly aligned. We just finally need to translate. So in summary, what we've done is we have rotated around, or we've rotated our z-axis, and we've rotated our up axis to align with z. We've rotated our positive e-axis to align with the positive x-axis. And then once that's complete, we need to translate. And we can do all that in one matrix equation, right? Okay, so I think probably an example would be helpful. This is all just, everything I've done so far is for visualization. And once we get that concept image, we like to do an example. So let's do an example. Yay for examples. Example. Suppose we have 2 points. This is going to be a rather lengthy example, and I'm going to go through it pretty carefully step by step. So 2 points, G and H. We'll just call them G and H. Such that G is at the origin of our ENU or LGH system. And then H is just some other point, right? So I'll just write, and H is another point in our ENU system. Coordinates of G and H, and we're going to ENU coordinates, are, so here's my point, and I have my easting in meters, my northing in meters. We like northings and eastings. We're used to working with those. And then my up value, which is like n plus h. Oops. So U, also in meters. And so G, since it's at the origin of our ENU system, of course, would have 0.000, 0.000, and 0.000, which just follows from the definition of the origin of a system, right? Our H coordinates are negative, easting of negative 1 to 6.348 and 839.609. And again, these are meters, minus 82 for my up, 0.598. So below the origin. And scoot up. I'm going to scoot this up a little bit and say further. Get rid of that mark. Further, H has geodetic coordinates, or sorry, G does, not H. G. That'll make things a little simpler. G has geodetic coordinates as follows. Phi of G is 40 degrees north, and lambda of G is equal to 80 degrees north, which we're going to want to work with, 80 degrees west longitude, but we're going to want to convert that to an east longitude and then to radians, of course. So 80 degrees, 0 minutes, 00 seconds west longitude. And the height is equal to 1,000 meters. And that's all we need in order to perform our rotations and the translation. Well, we don't have what we need to perform the translation yet. We'll get there. So what we want to do we will use GRS 80, ellipsoid, to calculate the geocentric or XYZ coordinates of each point. So we've used the GRS 80 parameters before. You could also Google. They're super easy to find. So GRS 80, I'll just write them down here. We have A equals 6,378 and 137 meters. And that's exact. I'll put 0.000. That's the definition of GRS 80. And the next parameter, the other parameter of the ellipsoid, remember that with modern ellipsoids, we're usually not given the B or the length of our semi-minor axis. We're given either F or 1 over F. Usually it's going to be 1 over F because it's more indicative of the definition of the ellipsoid as opposed to other ellipsoids. So for GRS 80, the 1 over F value is 298.257 222.101 meters. You know what? That's unitless. That's a unitless number. Okay. Now, from that, we need to perform some calculations. Remember that our goal is to calculate the XYZ coordinates from our easting, northing, and up coordinates, which requires the ellipsoid definition. So from 1 over F, so we're given that. So what we need to calculate is we need to go from 1 over F, which equals, let's see, 1 over 1 over f, which equals f. And that equals a minus b over a, which yields b equals a times 1 minus f. And that's just simple algebra. All I did was solve for b in this part here. So if I'm given a and I'm given f, or a and 1 over f, I can get b back, right? And then we need to calculate the square of our eccentricity, which is equal to one of the forms is 2f minus f squared. It also equals a squared minus b squared over a squared. And we need to calculate, and from that, of course, we take the square root. We have our eccentricity. Same thing with the e prime. Remember, we have this e prime squared, which equals a squared minus b squared. But this one is over b squared instead. So different ratio. And then we take the square root of that to get our e prime. So we would get e and e prime. That's super easy. So we go through those calculations, hopefully using a spreadsheet. Our goal is we need to, just to keep our eyes on the prize here, we need to compute the XYZ coordinates of our origin, our ENU origin, G. That's our goal, right? Okay, so we have all of our ellipsoid stuff. And what do we need to compute XYZ coordinates? Well, we need our n value, right? So we need n equals a over this ugly thing on the bottom, which is 1 minus e squared, our eccentricity squared that we just figured out, times the sine squared of our geodetic latitude of our origin, which we have, all of that denominator to the 1/2, or the square root of the denominator. Once we have that, then we can easily get x, which equals n plus h. We have h. We now have n times the cosine of the phi of our origin times the cosine of lambda of our origin. And then y equals n plus h times the cosine of our geodetic latitude of our origin times the sine of the longitude of our origin, right? And then z finally, and we have all these now because we figured our n. We were given h, phi, and lambda. So these are just simple calculations. Z equals n times 1 minus the eccentricity squared plus h. Pay close attention to the parentheses, where they lie in that. It's easy to screw up. Times the sine of our geodetic latitude of our origin. So we have everything we need to calculate our x, y, z. When we do that, in this example, we have x equals 849, 742, 0.781 meters. Our y is equal to negative 4,819, 130.9 0.784. And I'm going to subscript these so we know that they're of our origin. Meters. And the z value of g, the z coordinate of our origin, is 4,078, 628.360, and if you can, meters, and if you can think back all the way to the beginning of this lecture, all of that is our t vector, t prime vector, excuse me. That's our t prime vector. So now we have our t prime vector, we're ready to rotate and translate. And what are we trying to do? We're trying to create a way to convert all of our XYZ coordinates, or all of our ENU coordinates in our local geodetic horizon system, to geocentric coordinates, or XYZ. That's our goal. So I keep saying that because it's easy to get lost in the process, isn't it? If you remember, we just did two rotations. We did a rotation about the z-axis, and then we did a rotation about the e-axis. E-axis? No. Excuse me. We did a rotation about our e-axis, and we did a rotation about our u-axis. Okay. And what that is our... So our x vector, the thing we're trying to find, that's our x, y, z vector. That's what we're trying to find for any point, is equal to our rotation, our third rotation vector, in terms of gamma times our R1 in terms of alpha, and I'm going to define gamma and alpha here, times the ENU of any point we have coordinates for in our local geodetic horizon system, plus t prime, which is exactly what we did in the 2D situation, right? So I'll say where gamma equals minus 90 minus lambda, and alpha, they're just angles, right, is equal to 90 minus phi. And if we remember from the last video, we defined those rotation matrices, didn't we? So R3 of gamma equals, I'll do R1 first, I won't get screwed up with the order. R1 alpha is equal to, this should look familiar to you, 1, 0, 0, and 0 cos alpha, and minus sine alpha, and then 0 sine alpha, and cos alpha. That's our R1, where alpha is equal to this 90 minus phi. And our R2, and these are matrices, so is equal to, sorry, that's R3, is equal to the cosine of gamma and minus sine gamma. These should look really familiar. We just went over these last time. And sine gamma and cosine gamma and 0, and then just 0, 0, 1, where gamma is equal to the minus 90 minus lambda. Now, something that we could use is if we were to, we know we're going to multiply these matrices together to get a rotation matrix, a total rotation matrix. So I actually went through and multiplied these together, and the composite, so composite rotation equals, and I made it in terms of, you have to do some trig identity stuff and some fancy footwork with trigonometry, but I'm gonna calculate both ways so you can see that they're the same. So the rotation matrix, if you multiply that out, is minus sine of lambda, using the definitions we gave to gamma and alpha, cosine lambda. But this is much easier because now we're just using the latitude and longitude, right? 0. And then minus sine, this is the second column, phi, cos lambda. And then minus sine phi sine lambda. And cos phi, and then here it's cos phi for the third column, cos lambda, and cos phi sine lambda, and then just sine phi. And all that is just R3 times R1. So we have it all together. We can do it with one rotation matrix. So instead of R3 and R1, now we just have a rotation matrix. So again, we have, let's see, I'll change colors here. So we have our solution, which is X, Y, Z, or our X vector, is equal to R times our ENU, which are the coordinates we want to recompute, plus T prime. So when I throw that into a spreadsheet and print it all out, I can put my easting, northing, and up coordinates of point H in to this equation here. Put the easting, northing, and U of H there. I'll just put a little H subscript, which we were given. And we get X H equals 849,623.061 meters, and Y sub H equals -4,818,451. These are some big vectors. 0.818 meters. And our Z equals 4,078,049 and 0.851. And that's it. We've created our system. And if we had other points in our local geodetic horizon, all we'd have to do is plug them in to here and use this matrix operation to get our XYZ. So we've completed part of our process. We've gone from local geodetic horizon to geocentric. And remember, we have to go through the geocentric coordinates in order to get to geodetic coordinates, but baby steps, right? Now, I have taken that whole example and created a spreadsheet, which is posted on Canvas. Let me make this an appropriate size. There we go. And we start at the beginning. Here's my, let's see, I'll do it with this. So here's my ENU coordinates that I was given. And then my phi, actually this should be blue. Oop, wrong blue. There we go. So I was given my phi, lambda, and h of g, if you remember. So I just threw those into my green boxes and then calculated out my radians and then calculated the east longitude, which is what we want to work with in these computations, right? And I also put here's the green boxes under GRS 80 are what I looked up for the ellipsoid definition parameters and then calculated what my B value was, my F value, my E value, or my E squared and my E prime squared, and took the square roots, got those. So those are, here is all of the ellipsoid parameters that I need. And of course I have all of my equations here. So now that I have my ellipsoid parameters, I can calculate the n value of my point G. We're starting with point G, right? I also went ahead and calculated m, even though I'm not going to use it. And then you just used my XYZ formulae here, the n plus h, cos phi, cos lambda, etc., to get the XYZ coordinates of my G. And that becomes the t prime vector, my translation vector. And then I have my rotation angles, which are 90 minus phi here. And that's all I did was just, with the radians, calculated 90 minus phi. And sorry about that. I realized I have my notation wrong. It's phi minus 90, or my geodetic latitude minus 90. And then my gamma is minus 90 minus lambda. And all I did was just calculate that out with radians and then convert it to decimal degrees and DMS, just so I could see that they make sense. Now, here I have my R1 and my R3. Let's see if I can highlight those, which are the ones I'm going to use. So R1 and R3. And that's what I did. That's what I used here. I calculated out my rotation matrices. So just to prove that that composite matrix is the same as multiplying, here's the multiplication of my R3 times R1. And here is the result using just the composite matrix, which is, here's my composite matrix. And then I also, I did a difference so that you could see, yes, the difference is zeros. It's a zero matrix. They're all the same. So I have my rotation. All I have to do now is multiply my ENU here of H times my rotation matrix, and then add my T prime, which are the XYZ coordinates of my origin. And when I do that, I get just what I would expect for G prime, which is the translation vector itself. Those are the coordinates of my translation vector. They happen to be the coordinates of G prime in the new system. And then I just did that for H and got those values. So this is posted on Canvas. That's the process. And I think you'll find if you mimic this spreadsheet, it's actually not as intimidating as it sounds. Lots of symbols, lots of equations, lots of matrix operations, but it's not that difficult once you have it built. So that actually takes us, once you have that spreadsheet built, you can use it for assignment 3, and that now you should have everything to get through the homework. So that is matrix rotation. And when I post these, you guys probably realize that I blank out the formulae. So you can see I have formulae in here, and I'm never typing number. Once I type my givens into the green boxes, I don't type any more numbers at all. Everything else is cell references. All right. So I'm happy to go over this in Zoom sessions if you like. And if you have questions, of course, reach out, let me know, and have fun with this. It's kind of fun to build this spreadsheet, and then once you get done, you can compare the coordinates and see you got the same thing. It's kind of cool. Another thing, working with the matrices in Excel, that's something you really need to get used to. One thing I had to do was, since I have a row vector, that reminds me of something I want to talk about. Since I have a row vector here, and my matrix operation is defined, this has to be a column vector, I had to do a transpose. So over here on the side, let me just color that in. Where's my colors? So over here, if I were to try to, let's see, I'm going to go equals this, but if I need that to be a column vector, then I could turn it into a column vector easily by typing equals transpose, and then just highlight my vector, and it turns my row vector into a column vector. And that leads me to my last point, which when you are working with these matrices, and I do this every time I have a series of matrix operations, you really want to go back to here. Look at the dimensions. So my dimensions are, this is a 3 by 1. I'll use a by symbol. So this is a 3 by 1, 3 rows by 1 column. So that's what I need to end up with. So when I look at my matrix operation equation, this is a 3 by 3. This is a 3 by 1. So in order for me to get a 3 by 1 back, I have to add a 3 by 1 matrix. If you remember in the last screen in the Excel spreadsheet, I typed that in as a row matrix. So in my operations, I needed to transpose that anytime I wanted to perform a multiplication. So what do we end up with here? We have a 3 by 1 matrix plus a 3 by 1 matrix, which gives us a 3 by 1 matrix. I really strongly advise that you guys do this dimensional analysis on your matrices before you proceed too far into, before you proceed at all with your matrix operations or setting up your Excel spreadsheets, because it's really going to guide you into whether your matrix operation is going to work out or not. Okay, so super long video this time. But I kind of crammed two lecture videos into one. We had the midterm this week, so that took up a lot of people's time, and so yeah, that's it. Anyway, Let me know if you have questions, and I will talk to you later.